So this is the Cool K-PAC contest. So we have 3 finalists this year, and we're going to ask each of the finalists to come up and explain a bit about their K-PAC. So these are, I believe, to be real K-PACs that were authored within their companies in the pursuit of doing knowledge management. So this is the cup, and it's pretty heavy. So the winners will have their name engraved and company engraved on the championship, and we have a small prize for the 3 finalists. Okay, Josh, who's up first? Mr. Mayhew, fantastic.
Hey, thanks. Right, so I'm presenting this K-PAC on behalf of a guy named Gary Savidran, who's in our joining and sealing technical community of practice back at Navistar. So this is a K-PAC around elastomeric O-ring design, how you prevent extrusion failures, okay? So I have some graphics included in this in order to explain to people what extrusion failures are for O-rings. It's probably best if you scroll down past these and past the value table real quick. I'll get to that. Pause. Do you have the other chapters expanded? Let's look at the images. Okay. So what we do in our K-PACs usually is we go backwards from a particular failure, from what an extruded O-ring looks like, or what if you start to have some problems with this, that then works your way back into why is this an important topic, what is the design rule or design check that would have kept this from happening. So for example, we had done a number of, based on this guy's experience over the years and data collection, if you scroll to the bottom, I had mapped out the relationship between how you know when you can prevent O-ring extrusion failures. So if you scroll down to this graph here, what we had was, based on testing data, they had developed an interplay between fluid pressure and total diametral clearance, which was how tightly basically the O-ring fit in there, and then developed different curves around the hardness of the O-ring. So forgive me, this is not entirely my area. But basically part of the issue we had when trying to convey this to people was that this chart, just as a chart, is not yet active knowledge, right? And what if I was in kind of a close case? Like let's say I'm 0.4, but I'm like 950. Am I above or below that blue line? Well, I don't know. Let's go ahead and try it and find out, right? So what we did with a guy in our group named Rick Ridgway, who couldn't be here today, is he reverse engineered the curves and programmed them into the value table. So if you scroll back up, basically you'll see the contents of the expressions inside of the value table. Don't worry about that, because all you have to do as an engineer is click the lightning bolt. You click the lightning bolt to evaluate the K-PAC, and let's say, for example, I'm designing a joint that has 400 psi fluid pressure, and the O-ring that I'm using is of a 70 material hardness in Shore A, but I'm using a silicone O-ring, okay? And with this particular joint that I have 0.3 mils of clearance. So it's fitting in there pretty tightly. And then I would resolve this K-PAC. So what it does is, based off of the way the curves were conveyed and the reverse engineering of the curves, then we were able to calculate basically, what do you have versus what is it that you actually need? You have 0.3, but that's a little too much. It needs to fit in there a little bit tighter. So you can see I either need to close the joint up, or as another design alternative, I could switch the material selection from one kind of O-ring, a silicone one, switch to the other of a medium shear modulus material, resolve that, and that would tell me, yeah, now you're passing, right? So this is to me, a good example of where we took something that was based on a ton of this guy's experience, and he was really good about, this guy will spend all day with you explaining sealing design with you, and he had all of these pictures, want to load all of the knowledge in there. But then how do you convey that just through that chart, and how do you tell if you're above or below? So we just said, let's activate this up, and I know we've used this in our assessments there at Navistar.
Okay. Very cool.
Thanks.
Definitely a cool K-PAC. Josh, who do we have up next? Jerry, you want to come on? Or Jerry, come on up. Jerry's from General Motors. Looks like we have some similarity.
Oh, Jeff. Jeff.
Jeff.
Hi, my name is Jerry Hanson from General Motors. This is going to be similar to what Jeff did. Value table is not quite as fancy, but it's delightfully simple in its calculation of a pretty complex system. So what I got was, I don't know, somebody from, I think it came from Brazil, emails me this chart down here on the left and said, we want this in Auros. Great. What does that really mean, right? Do you want just a picture and a dumb value table? So I didn't want to do that. And one thing we do, and if you were here last year when we presented, we use Auros to configure and drive all of our KBE applications in NX so that we don't ever have to recompile and redistribute when we want to make changes on the fly. So we use Auros as the back end or the front end for all of that kind of stuff. So I had to have something that would rule process, much like Jeff's, but I also had to have something that I could run into NX, create rule features in the part navigator, and then rule check against those and feed back to the designer whether he was going above or below the lines or whatever he was doing. So for those of you engineering degrees, guys, okay, you're familiar with the slope of a line, y equals mx plus b, right? So when I had to have something, go ahead and poke that picture up again. I didn't want to create a value table that just was one for each line because then I didn't have any variation in between. So go ahead and close that and then pop up the value table. If you look here, what you really have is y equals mx plus b, but there's three other y equals mx plus b equations that run this one. So the result is a very simple, not simple, but one equation based on the bend angle and the hose ID that feeds then back to the CAD tool or to the designer. I mean, you could run the lightning bolt, run the rule processor, again, and do the same thing. Go ahead and go back to details. So then what we do in NX is we run this, we create a feature in the part navigator. We happen to go under bar one, because right now if you do a one-to-one map, and Jeff will remember this, you can only have one rule processor against that particular feature. So we create a bunch of expressions in NX timed to that same rule, so we can have a bunch of different values checked against that one rule in NX. So this one equation then solves an infinite number of bend angles in our CAD files. So that's really what this thing does, is it feeds the whole NX system, and we have an application that runs off this. And and there's more than this one. I mean, we've got some that have curves, and we have some that do solid things, but point is the application then just reads these K-PACs and then makes their life much simpler, so. All right? Jeff?
Oh, thank you very much. Can we rule process against it? Can we run the rule processor against it? What kind of values can we use?
Well, I mean, it really doesn't matter. Just type in 55 degrees or 45 is fine. A hose ID of 2 inches or 50 millimeters.
15?
Yeah. And then just what the hell do. And they'll come back and fail because it says the minimum bend radius of that particular angle and that particular hose ID has to be a minimum of 22, 22.1. And it's good for all those ranges so you're not just stuck on the one line. You can do any range. It could be 55 degrees, 57 degrees. It's solved. Now there's quite a lot of magic that happened for me to get to that. There was a whole bunch of work just to simplify that equation down to that.
It's awesome.
But yeah, it turned out pretty well, I think. So.
Very cool K-PAC again. Thank you, Jerry. Tom. From ZF.
No music.
No music, sorry.
I need the music. So I'm privileged to introduce our ZF Cool K-PAC. Actually, not to burst everyone's bubble, but this K-PAC's not in production in ZF. It's really just the demonstration of the whole process that we have for decision making. So, but the format is essentially what we would see in all our K-PACs. We have a lot of multimedia to take full advantage of that. In fact, if you open that, if you remembered what we talked about before, the decision process requires criteria, assigning values, and then we use all our little thumbs up knowledge to come up with the decision in the end. Of course, instructions are in there. Scrolling down, I'll get to the value table in just a second, but at the bottom, Of course, there's a lot of references. Wikipedia, unfortunately, I referenced it, but information about fuel economy, of course, the quote about the every color except long as it's black is all there. But all of this is really neat, but what was cool about this K-PAC is really in the value table. So actually, if you can edit and open up the value table, just kind of go through it. Oh, you got it. Perfect. So, and I have to say, once again, we had all this in Excel, but I have to thank Josh and Jimmy for actually coming through and showing us that we could do this all within Auros. And once again, the value is to have everything in one tool and you're not switching back and forth. So the first 4 columns really are introducing the input of your criteria, the low cost, maximize fuel economy, utility, and wow. And I'll get to why there's 2 rows here in just a minute. After that, I essentially calculate, based on that criteria value, a raw ranking. And that's how many thumbs up there were. So it's essentially how many thumbs up times the criteria. And then we get to the input as far as chartreuse, which now I'm finding more people don't really know what chartreuse is, but that's another story. So in the K-PAC itself, I needed to have a line for yes if it's chartreuse or no. So it needs to calculate that the formulas for both situations. And then obviously, whichever one you choose, you'll get the answer in the end. The next 4 columns are essentially the way I can exclude certain design alternatives from the pool. And the bottom, if it's chartreuse, is no. That means all of them receive a number of 1, and so they're all accepted in the pool. If I wanted yes chartreuse, then you know the Model T has to be out of it. So essentially, it gets to 0. So then the final 4 columns is now a ranking calculation of the raw ranking that I had initially times that multiplication of the 0 or the 1. That's how we can exclude certain criteria from the decision-making pool. And then the last section, the derived value, essentially I want to be able to return a string. I don't want a number going into our CAD program. I need a string, saying our piston's going to be steel. It's going to be phenolic, whatever it is. The number doesn't mean anything for us. So this is essentially just, I know it's gobbled, but it's just a nest of if, then, and else's to come up with that string. Why don't we go back to the lightning bolt? By the way, that's all one decision. We actually use assessment controls to house all of our decisions. But unfortunately, you don't have a coolest assessment control. But, so if we throw in, I think 10, number 10, the number 3, and 3, and 5, and right now we'll say no chartreuse, and then we do the resolve. I think the answer down below, we're actually getting our car choice as the parameter that we're getting is Model T. So now if we go ahead and change chartreuse, yes, we like chartreuse, and hit resolve again. If you scroll down, it better have changed, yeah. So now the next selection, the next highest ranking is electric car. In fact, if you want to do one more, Josh likes sports cars. He doesn't care about cost. He doesn't care about fuel economy, so give it 1. Oh, yeah, do 1 for the top one. You don't care about fuel economy, give that a 1. And utility, you don't need utility, you have a 1. But give it 10 for the wow. Hit resolve. Yeah, you like chartreuse. And it better be a sports car. Okay. That's our coolest K-PAC.
Fantastic. Thank you, Tom. Okay, it's interesting. There's many different types of K-PACs, and this year's finalists all have fairly complicated value tables that encode decisions that ultimately involve derived values, which is interesting. So intermediate into qualifying anything or providing a pass-fail, there's a derived value in all of these. So there's a bunch of calculations being made, and the derived value is being passed on to something else. In this case, the derived value came out to be a string, which was the type of car. Fantastic. Thank you all. So now what we're going to do is we have to decide who gets the name on the cup. Everybody gets, all three participants get our finalists get a prize, so that's okay. So what we're going to do is we're going to open it up to open polling. So if you could please now vote for which K-PAC you feel was the coolest. Thank you. When we're done voting, we're going to ask the finalists to come back up here, if you don't mind, get a picture and get your gifts for participating. I got to say, it is a tough decision. It is a really tough decision. I'm not going to vote, but I'm not sure who I would have voted for. They were all really, really good. They were all really good. You can if you want. Let's see. And the results are... Oh my God, is it close? Mr. Mayhew, it looks like you won. But can we have all three of you come up?